Okay, so this is going to be our last section of math that we're going to have to do. So all these notes are going to be on titration, so I would highlight if I were you or write down the stuff. So the fancy word is titration. That is a type of lab experiment you're going to do. Now it's still 8.4, so a titration is still a mixture. Okay, so you're still mixing acids and bases with each other. So you're still going to follow the rules like we've been for when we were mixing stuff. So in titration, here is the definition for it. So for a titration, it involves the use of known concentration of base to neutralize an acid of an unknown concentration. So that's what we're going to be doing. So the word is neutralize. The most common one is with a strong acid and a strong base. Okay. And so the reason why you do this is because you're given the concentration of the base, and your goal is to find the concentration of the acid. Okay. So let's say you have a bottle of vinegar and your titration or your goal is to determine how strong is that vinegar. So there are some key words here that you're going to see. We're going to do a practice College Board FRQ when we get back. So the word titrant. Okay. So a titrant is a solution of a known concentration. So this is the one that we know of. Okay. And it's the one that's going to be in the burette. Okay, so I drew a little drawing here. You guys seen this setup before. So here is the drawing, and then here is the little valve. You know, you all like to joke around and call it something else. But the titrant is in the burette, and you're going to have to know that. Okay, the analyte, okay, that's the one that's the unknown concentration, and that one is going to be in the flask. Okay, so I drew my little flask here. So basically you have the burette with your known. Typically we put a base in here. It's usually sodium hydroxide. We know the concentration of it, and you're going to dispense it into the Erlenmeyer flask that is down below here. In the flask is going to be some volume of acid that we don't know how strong it is. And so when it turns that color change, then we stop, and then we can do some math for it. So the goal of it is to basically get the change in volume, because then we can use big M equals moles divided by liters. Okay, so we have the titrant and the analyte. And I like to think of it too as this one is the one that we're analyzing. Okay, and it kind of sounds like it. So it's the one we're trying to figure out. The equivalence point, sometimes it's known as the endpoint. That is when the moles of the base equal the moles of the acid. And that's going to help us with our calculation. When that happens, you need to know that at the equivalence point, there is a color change. Most common one, now there could be different colors, and we'll talk about that in our last section. Typically for us, it's going to be pink, because I like to use the indicator that causes it to turn pink. Okay, now you heard me say the word indicator. Okay, so that is going to be the one, you're going to put a couple drops of it into your flask before you start titrating the base into it. So that is just a substance that changes color with pH. Okay, that is basically, I kind of like to think of it like food coloring a little bit. So you put it in there, and once you have your equivalence point, it's going to turn a color, and in our case, it's going to be pink. Okay, for example, there are many different ones which we're going to read about. The most common one, or the one you're going to do for your lab next week, is called phenolphthalein. Okay, so that one's the one that turns pink. I think this, I can never say the beginning of it, but this one down here, the prothymal blue, I think it starts yellow and then turns blue, and then methyl red, I think goes from orange to red. I could be wrong. There's a whole chart for it. It's not like you'd have it memorized or anything like that. This down here, we're going to talk about this because typically for a titration, you want to pick the right indicator. For our case, we're going to do phenolphthalein because we're going to do the strong base with a strong acid. But depending on what you're mixing, there's a little chart that you can read that tells you what indicator is the best. Okay. And you always look at the pKa. Okay. So usually that value is given to you. Titration curve. Okay. So usually when you do, I'm going to fold this. So hang on. When you do a titration, you get all this data, and usually you get some kind of curve, and it's just a plot of the pH. So it kind of shows you where the pH started and then where it ended. Okay. And for this thing, you're going to use, you will learn that methods for finding pH at various points during these titrations are going to be different. Okay. So here are the ones that you can do. So you can have a strong acid with a strong base. We learned that last week, and hopefully you remember that is called a neutralization reaction. Okay, so I remember since it's still a mixture, you're just titrating it because you're using that fancy burette. You always use those equations that are on the green sheet that I gave you. Okay, if you remember for a neutralization reaction, we always have our acid. Remember, our acid is usually associated with H plus. Then we have our base, our strong base, that's usually associated with OH minus or hydroxide. And typically you form water. And then if you remember, it forms water in something else, some kind of salt. And remember, you can put that down the sink. Okay, so that's when you have a strong acid with a strong base. So the curve is going to typically look like this. Okay, so for these pH, these titration curves, it looks like this. It kind of looks like a curve, I guess you could say. The pH is always on the y-axis, and then you have your volume of base that you added. Okay, so how to read this, if you notice, it's kind of like reading a book from left to right. So your pH starts down here, and I would say that kind of lines up with almost close to 0, right? I think it's like kind of like at 1. So that means when you analyze this, this is the stuff that is going to be in the flask. So this is your initial pH. So this kind of tells you that, oh, hey, we started really down low here. So that means that there is a strong acid. I can't see that. And that's the one that's going to be in the flask. And if you remember from up at the top there, if it's in the flask to start with, that means that's going to be our unknown concentration, and it's going to be our analyte or analyte, whatever you want to call it. Okay. Then you notice that we start adding base to it, so that means our base is going to be in the burette. You notice that now the pH, I'm just going to highlight, I guess I'll highlight with a different color. Our pH slowly kind of like increases a little bit. Right here, we have more acid than base, so that's what that's showing, right? Because it still has a pH less than 7. And then as you're adding your base, it's starting to rise. Then you get to right in the middle, so you kind of have like from here to here where it's sort of like, I want to say it's a straight line. I know it's not exactly a straight line, but right in the middle of it, that's where you have your equivalence point. And when you have a strong acid with a strong base, the pH is going to be 7 because it's neutralization. Okay, and then it's still increasing. You're adding your base, you're adding your strong base. So that means your pH should be pretty high when you end it. So this is going to be our ending point on the curve. And you notice it's a pH greater than 7. So that means you were adding base, obviously, and then it turned basic. Okay, so that's what it would look like for a strong acid with a strong base. Now, if you don't have two strong ones that you're mixing together, then obviously the curve is going to look different. Okay, so that's that page. So let's flip. Okay, so now the other option you have, what if you decide to take a weak acid and mix it with a strong base? Okay, so the curve is going to look a little different than the one we just had on the front. Okay, so again, when you read these curves, pH is always on the y-axis, and then we had the volume of our base. This time it was NaOH. Honestly, it could be any base, okay? It has to be a strong base because this is the example, but this time we pick NaOH. So your pH curve, do you notice that right here where we initially start, it's not 1 or 0, okay? So that should be an indication, because if you get a question like this on the test where I say, hey, is this showing a weak acid or a strong acid? And you should be like, well, the pH is roughly, is it going by ones, 1, 2, 3? Okay, typically that's going to be kind of weak, right? Because strong acids are either going to have 0 or 1. Okay, so this right here, our initial pH is for a weak acid, which I say right here. So it's a weak acid. Now, where you start, that's what's in your flask. Okay, so that's our unknown. Okay, and that's going to be called our analyte. Or analyte, whatever you want to say. Now, it's saying, hey, we are going to start with a weak acid, and we're going to add some base to it. So as you're adding the base, you're going to notice, hey, this pH is going to start going up, right? Okay, so, and then it keeps going, and it's still a strong base, so that means we're going to end up pretty high up here. So that's where we're going to end. Okay, we're going to have a lot of OH left over because it doesn't neutralize, right? Because it's a weak with a strong. So you're going to have a lot of base left over. Now, before on the other one, when you had two strongs, the pH was 7 at the equivalence point. This time, the equivalence point is going to be a slightly higher, and it's going to be in the base range, right? Because if we have a strong base, the base is going to win compared to the weak acid. So you're going to notice that here's 5, 6, 7. Typically, on the other graph, the equivalence point was right here. But it's not. It's going to be a little higher because our equivalence point is going to be in the middle between our kind of straight part right here. So it's going to be a little bit higher up than 7 because the base is the strong one. Okay. Our pKa is going to equal our pH at the equivalence point. Okay. So that's something also good to know. I even say it down here. You might want to highlight it. Note again that for a weak acid and strong base titration at halfway point, our pH equals our pKa. So if you know your pKa, you can say, hey, that's going to be our pH at the equivalence point. Okay, I put this down here. pH at equivalence point is higher than 7, so that means you had a strong base. Be able to prove this with an ice table and a pH graph. Okay, so if you notice, I kind of drew them out. This is my drawing, so I'm not the best, but if you notice, we already talked about the strong acid with the strong base. So that's what this looks like. And remember, in the middle here, at our equivalence point, pH equals 7. And then let's say you start with a weaker acid, but it's still with a strong base. It looks a little different. They sort of like end the same, okay, right? Because it's a strong base, but your weak acid starts higher up. So that means our equivalence point is going to be kind of where it's a straight line. So we'll say like roughly here. So you can see the pH is going to be basic more. Okay, now that's going to equal our pKa. Obviously, we have no numbers here, so I'm just going to say it's probably going to be bigger than 7. Okay, I'm going to flip the page. Okay, what happens now? Let's make the base weak, right? And how about we have a strong acid? Okay, so this time, if you notice when we read our graph here, our pH is still on the y-axis and our volume is now on the y-axis. But do you know this time it says volume and it says HCl. So this time we're going to add acid. We're not going to start with it. We're going to add it. Okay. So if you notice where we start here, we don't start down here like before. We start up here. That pH is going to be greater than 7. So that means this guy is going to be a weak base. Now, if it was a strong base, it would be more up towards 14, okay? So this is a weak base. Now, this one is going to be in our flask this time, and that's going to be our unknown, and we're going to say that's the analyte, okay? Now, we are going to put some of our acid in the burette, and we're going to mix them together. So if you're adding acid, you're going to notice the pH, hey, you better start going down because we're adding acid to the solution. We're going to keep going, keep going, keep going, keep going, keep going. Okay. Now, at the end of it, you notice that it ends right here. That means that's a strong acid, right? Because look, it's I think on 1 exactly, or close to 1, right? So that means a strong acid, so it became very acidic. Now, our equivalence point is going to be acidic, right? Because you're adding a strong acid to a base, okay? So if you're adding the strong acid, the acid's going to win because you keep adding it, it's going to turn acidic. So it's going to be less than 7, okay? So we started with our base and we added our acid and that's what we got. Our equivalence point, again, is going to be like in the middle or straightish line a little bit, you can say. So it's not 7. At the halfway point to the equivalence, the POH equals the pKb. Okay, so before we started with our acid and then we said our pH equals the pKa. Well, since it's a base, it's going to be the pKb. Okay, you're still going to have to do maybe an ice table when you have to prove this stuff. So I show 2 graphs here. So here's our strong base. This one is starting with a strong base, so we're really, really up high on the pH. And then we're going to add acid to it. Why? How do we know we're adding an acid to it? Because you notice the pH goes all the way down and it ended as an acid. Then for our weak base, we're going to start a little bit lower. We're going to add acid. How do I know? Because the pH or the line is going down, okay, towards less than 7. Okay, so I'm going to flip the page. What do I have on this side? Oh, okay. College Board slightly hits on this. So a polyprotic acid, poly usually means more than one. Okay. So for a polyprotic acid, it's going to have more than one H. So more than one H. I say for polyprotic acids, titration curves can be used to determine the following. So you can determine how many acidic protons you have. Remember, in our acid-base unit, protons are H pluses, right? So it can tell us how many H pluses there are. So that's really good information. It can tell us the pKa value, okay? And it can tell us about different things that might be present, okay? So for instance, right here, if you look at this curve, I like to say there's kind of two of them. So we have one, and then we have two. Okay, since there's two, I would say there's probably going to be two H's. Now, if it kept going into a third one, then there would be three H's. So again, the equivalence point is between. Okay, so that's for the first one. And then for the second one, we have our pKa's that we can determine from the graph, and it kind of gives us the pH's. Okay. Okay, we are going to do more math, but I'm going to do that in a separate video. What do I have here? I'll leave it for the separate video.